These are different mappings of basically the Milne model of the universe. Um, the let's see, I want to try to remember what George Dishman calls them. Okay, here are George's coordinates, what he calls them. The SR coordinates, proper coordinates, co-moving coordinates, and conformal coordinates. And here were some, well, these were my suggested names for the map as Paul would describe them. The original Milne map, the original ruler observer map. He didn't give me a name for this one, and the co-moving original map. Okay, re-looking at this map, I need to make a change to it because these lines are not supposed to become bent as you go down. There's a couple of different ways you can make this light cone straight. For me, I really didn't care about making those times straight or keeping those instants straight, so I just kind of allowed them to drop. Actually, it's almost the reverse of what they do on here, because as you go outward, they become more and more in the future. On this one, those same events become more and more in the past. And then I had my labels that I can't even read on this scale, so let's see what I can do. That one is the kinematic Big Bang in Minkowski coordinates. This one is an isomorphism of the Minkowski region, prioritizing the proper length of the green lines in the horizontal representation. And actually, I have been more recently kind of taking back this word, proper length, because I feel like that is, I wish I had another name for it. It's mind control through the use of words. By calling this the proper length, it is an insult to the length that is given over here. This is the actual proper length, or the proper length over here is determined by x. This, by calling that the proper length, it's uncorrecting a concept that you should have, which is that over here, this is the Euclidean distance between the lines. Basically, the distance between those blue lines there is the Euclidean distance, and that is for simultaneous events. That distance along those red lines is the proper length. The distance here along these green lines, that's an improper length. You're just taking something that is not a proper length, which is kind of this angle here. Those green lines are represented over here by those green lines, and these are not simultaneous events. We've tricked you into believing that they're simultaneous events by pointing out that all of these clocks will have the same time on them, but really having two clocks reading the same time does not make those events simultaneous, because we know we live on Earth where you travel a few hundred miles and you're in a different time zone, and the fact that the time on one clock matches the time on the other does not make those events simultaneous. In fact, if they're set to the correct time zone, generally uh, clocks can be off by as much as 24 hours. The reading on the clock is not what makes the event simultaneous. And so this coordinate system where these clocks are simultaneous does not make them or have the same reading, does not make them simultaneous. Here I have something called rapidity pseudospace. These are the Hubble observer pseudo coordinates from rapidity and proper time. I'll uncover, I think I should uncover that tau in both situations. I'll put that here to label that. I can't fit it over there, so I gotta put it here. We'll use symmetry there. Anyway, this is the isomorphism. So this is tau phi. Here we've got tau and phi. So the rapidity is kind of a labeling of the particular objects. So this this guy's rapidity is 0, then maybe this guy's rapidity is 0.1, 0.2, 0.3, 0.4, etc. Actually, no, I've actually got the numbers down there. So this is definitely rapidity of about 1.2. So I don't know how I subdivided those, but each of those is a rapidity labeled down there by 1, 2, etc. And then finally this one, defining pseudo coordinate, I forgot what that was, upsilon actually, to make past light cone seem straight in rapidity pseudo space. So that is basically stretching out the the lines, these constant time tau lines, to make it look like this light cone is straight, so that the speed of light in those coordinates are straight. So I'm going to come back to this one, even though, I mean, the only big change that I would make to this is to say that here, the x is a distance. It represents the Euclidean coordinates. And because I like words to have actual meaning, I also want to say that when I'm using Euclidean coordinates, these are also the true proper coordinates. The distances here represent, the distances along the x-axis here actually represent what people would think of as distances in in the uh, in the real universe, in the real Milne universe. Here, though, this thing that is called the proper coordinates traditionally is actually a sum of non-simultaneous distance measurements. Basically, you're looking at a whole bunch of rulers at different times, different Euclidean times, uh, putting them, and what we're going to do is we're going to measure as though, well, you know what? George has posted a picture a few times, and I've never gotten around to actually showing it on my screen. Okay, this is the key here. Co-moving distance coordinate, d0, is the proper distance to an object measured in the manner we discussed previously. Reminder diagram attached. So this isn't the first time. This is from page 4 of the discussion. So he did post this diagram at an earlier time. The time parameter in the co-moving coordinates is proper time. So what he wants to do, now I could go back to that earlier discussion, but what I want to do is kind of take a copy of that and put it down there, and maybe even another copy somewhere down below. We need a speed of light line in this. I'll just put it here. Where is that event being taken into account? Okay, the idea that I'm kind of interested in here is the Einstein synchronization convention, which is basically looking at, when does this event happen? When does this event happen? Those those two events are observed somewhere up here. So actually, no, actually what I want to do, I guess that event and that event are not simultaneous. They're observed somewhere right there. And that's the halfway, that should be the halfway point of the ruler measured. Actually, it probably really is going to be somewhere around there, I would think, if these lines are drawn drawn correctly. So the speed of light is equal in both directions. So that's why this has to be a different time than this event here. And so the event of measurement for these two coordinates, let's draw lines for that too. We'll have the event of measurement. So this is when this observer sees this event and this event. And then this is when this observer observes that event and that event. So there's also going to be further, there's going to be more rulers. Each one, I'll just kind of sketch this, but it's going to be a higher slope. And again, we can draw the speed of light lines. And that is when that observation will take place. So all of these events, the measurement of this ruler and the measurement of this ruler and the measurement of this ruler all take place at different times. Now the clocks might read the same thing. The tau equals 5, tau equals 5, tau equals 5. But this guy is definitely going to say that this event happens after this event, and this event happens after this event. So this is the first ruler measurement from his perspective. That's going to be different if I do the Lorentz transformation. This guy is going to say, I made the first. He's going to say, I made the first measurement. This guy is going to say, I made the first measurement. That's how the Lorentz transformation works. It actually changes the it actually changes the ordering of the events. So he says the time parameter in comoving coordinates is proper time. And I'm saying the quote proper time parameter is actually not proper at all. It represents the time on a bunch of non-synchronized clocks. Okay, later in the same post, George Dishman said that he thinks that I have missed the definition of A of t, and by the way, the discussion of A of t is changing the subject. This is not the definition of A of t was between here and here. And it's really rather ridiculous for him to be saying that I've missed the definition for A of t, because this is after I have gone from here to here. I specifically used A of tau equals 1 over tau to go from there to there. For him to say that I've missed it is rather ridiculous. He says the physical meaning of A of t equals t over t sub naught in Milne's model is that all distances are increasing linearly with time and were 0 at t equals 0, so it is the one factor that fully defines the motion of all his dots. And that's just absurd. The physical meaning of A of t, where it was applied here, first of all, it's not t, it's tau. And secondly, it has no physical meaning whatsoever. There is nothing physically that has happened to this in changing this coordinate system. There is nothing, there's no physical meaning to this at all. There's no distances increasing linearly with time because of A of t or anything associated with that. All distances were already increasing with time here. And they were all at 0 at t equals 0. That factor between here, this mapping and this mapping, has absolutely no effect on the physics at all. So once again, the mappings from x comma t to tau t phi to tau phi to tau comma curly upsilon coordinates have absolutely no physical significance whatsoever. The increasing distances, starting from delta x equals 0 at t equals 0, are already present in the Euclidean coordinates, the true proper time, without any application of any scale factor. So George's claim that the physical meaning of a of t equals t over t sub naught, this goes from here to here, is that all distances are increasing linearly with time, and we're 0 at t equals 0 seconds. So it is the one factor that fully defines the motion of all his dots. No, this doesn't have anything to do. This scale factor between this coordinate plot and this coordinate plot have absolutely nothing to do with any physical meaning of the motion of these guys apart from each other. Because in Milne universe, this is not the proper coordinates. This is the true proper coordinates in Milne's model. This is not. This is just sort of a something you can do with math if you really want to. But there's no reason, no physical reason to go to this map or this map or this map within the context of Milne's model. So here is kind of how I would try to represent the nature of the debate, is that I think that this represents the Euclidean coordinates, and this is actually the only version of things that I would actually call the Milne universe, because this represents space. The x coordinate here represents space, and these other things, tau phi, those don't represent the distance. So those don't represent the true distance between points. This one, George's Euclidean coordinates, he really thinks of these measures of these green lines here being the distance. And he sees those distances as increasing over time. And he sees some kind of fundamental importance of the scale factor that exists between this map and this map. And he thinks that the reason that these things appear to be moving apart is because of that scale factor. Now, Paul, his description of the reality is mostly concerned with this, and he thinks that this is the real Euclidean space. And in that context, you see these blue lines kind of coming together over time. That kind of represents a shrinkage of the actual bodies in space. And so I think the question I've been asking Paul several times about Euclidean coordinates is that he would think that this phi variable here is the actual distance between galaxies, which is not shrinking. Now, that might not be the case. It might be that George and Paul can't be pinned down to that point where they would say, yes, I agree that this is the Euclidean coordinates, and this, or George might not say, yes, I would agree that this is the Euclidean coordinates. They might have the sense that Euclidean coordinates simply don't exist, or maybe they just aren't willing to pin themselves down to that level. But I am definitely willing to commit to saying that this x variable here, these blue lines, represent sort of a Euclidean coordinate system, a set of Euclidean points. And those Euclidean points, of course, are Euclidean points that are stationary, so they do have that time element. They do have duration. Well, I hope that clears up something. Thanks for watching.